Hello gentlemen, purpose of this video is to study the natural logarithmic function, which is actually the inverse of the natural exponential function. So let's get started here. Let's take a quick look here. So like I said, the inverse of the natural exponential function e to the x is denoted ln of x, or the natural logarithmic function. Okay, and again, let's make some use of the fact that these are inverses of each other um, to look at the graph. And just some notation here. Ln, as you just saw in that previous note there, the ln function is really just another logarithmic, but it just has a different base. So I'll write this out. So we have log base e of x. That's the log with the base of e. We're just going to write that as ln of x. Okay. And so this is going to be the representation. You see an ln button on your calculator, and that's what it is, the natural logarithmic function. Understand that these are inverses of each other, and so the domains and ranges are switched. So the domain of this function here, the domain is going to be 0 to infinity. The range is going to be all real numbers, okay, which is the opposite of this function, okay. The horizontal asymptote for e to the x, which was the x-axis, is a vertical asymptote at y equals 0, okay. I mean at x equals 0. X equals 0 is a vertical asymptote, okay. Increasing and continuous, just like e to the x. This is the point 0, 1, and on the inverse it's 1, 0. Okay, so again, these should all make sense, and we have a reflection across the line y equals x. Let's look at some properties of the natural logarithmic function. Ln of 1 is equal to 0, which means that e to the 0 is 1, which we know. These are very similar to the ones we did for a regular logarithmic of base a. Ln of e is equal to 1, which means that e to the first power is simply equal to e. We know that these are true, again, because of inverse properties. Okay. Remember, for inverse properties, we had, if f and g are inverses, f of g of x is equal to x, and g of f of x is equal to x. All right, so those are two properties that are for inverses, and we already know that. This is the one-to-one property. Okay, if ln of x is equal to ln of y, then x is equal to y. Right? And so again, let's do some more practice. If I have this is the logarithmic equation. If I want to write that in exponential form, it's simply 3 to the 4th is equal to 81. If I have ln of e is equal to 1, we know that that means e to the first is equal to e. If I have log 1 over 1,000 equals -3, remember, if I have nothing here, we're assuming that we have a base 10 here. Okay, so this is going to be 10 to the -3rd equals 1 over 1,000. Let's do it the other way. Let's write the exponential equation in logarithmic form. And so if I have 9 to the 3/2 is equal to 27, that means that log base 9 of 27 is equal to 3/2. 4 to the -3rd is equal to 1 over 64. That means that log base 4 of 1 over 64 is equal to -3. Hopefully you guys are seeing the relationship between the exponential and the logarithmic forms. E squared is equal to 7.3890, etc. That means that ln of 7.389, etc. is equal to 2. All right. Let's look at sketching a graph. Again, we've done some stuff in the past, but what we need to know is here, you know, what is my domain range, what's going to happen to my intercepts, etc. If I look at this here, this part right here, this right there, is going to tell me that I'm going to get a horizontal shift to the right, 1 unit. That's going to affect my domain. All right. So my domain of the ln function was 0 to infinity. Now my new domain is going to be 1 to infinity, okay, because I shift everything to the right, okay. If I'm thinking about the range of the ln functions, all real numbers, that's not going to change here. Okay, that's not going to change at all. I do have a vertical shift, this +4 here. That gives me a vertical shift, and that's going to be upward, up 4. Okay, so my graph is going to shift to the right, 1 unit, up 4. It's also going to move my vertical asymptote. My vertical asymptote, instead of x equals 0, is now going to be the line as x is equal to 1. Okay. The other thing I want to point out, let me get rid of some of this stuff, is how do I find the 0, the x-intercept now? Okay. That's going to be different than before. And again, I can do that by setting the function equal to 0. And that's not too bad, so let's do that quickly. If I set the function equal to 0, I'm going to get that the ln of x minus 1 plus 4 is equal to 0, which means that the ln of x minus 1 is equal to negative 4, like that. And now let's write this one in exponential form. And if I write this in exponential form, I'm going to get x minus 1 is equal e to the negative 4th power, like that. And then what I want to do is just solve for x. X is equal to e to the negative 4th plus 1. And so that is going to be my new x-intercept. Okay? I can put all those pieces together. Let me get rid of this. Hopefully that makes sense to you. And we can make a graph here. Let's get rid of this. All right. We've said we moved our vertical asymptote over x equals 1. Here's my vertical asymptote. Here's my new x-intercept. Okay, this is the line here. X is equal to 1. Okay, everything got shifted over this way, 1 unit, and this way, 4 units. Okay? Hopefully that makes sense. And again, this is just going through our basic transformations that we learned about way back in Chapter 1. Here's some more practice. Here's some examples I want you guys to take a look at. Some problems. I know that seems like a lot. Many of them are straightforward. Basic part of this video that we introduced the natural logarithmic function. We looked at its properties and its relationship to the natural exponential function. Okay? Any questions, make sure you guys are emailing me. Have a nice day.